Hi, can you hear me?
Yes, sir.
Okay. Okay, so we can start. So I sent the problem sheet for today earlier. I hope you got a chance to try the questions. So you won't have to spend time in the lecture to give you a chance to attempt the problems. Okay, so we can go in order, starting with the first problem. Anybody who has already found the solution to that?
Yes, sir.
Okay, just a minute, let me check if others have also tried it. So others, did you try the question and you didn't get it, or you didn't get a chance to try it at all?
Sir, I couldn't attempt the problem set.
Okay. Yeah, it would be good if you attempt in advance, because then we don't have to spend time in the class giving you some chance to try it, right? So yeah, Arnav, what is the answer?
Yes, sir. Just a second. So I got the value of n to be 315
Yes, correct.
and the 3 plus 1 plus 5 9.
Yeah, correct. So this is a very simple number 3 question. All that we're asking is that if you have any 7 consecutive odd numbers, right? So like 2k minus 3, 2k minus 1, 2k plus 1, etc. Plus 9. Don't know why I started with 2k minus 3. I thought it would be symmetric, but it's not the case. But in any case, if you have 7 consecutive numbers and you find their GCD basically, then what are some factors which are guaranteed to be part of the GCD? So just by simple observation of the first few entries, you can see that obviously you're looking at some kind of prime factors. So if you just consider the first few prime factors, 2 is obviously not considered because these are odd numbers. There will be at least one copy of 3, and in fact, if you think about it, there will be at least 2 copies of 3 in this series, because basically you can look at them in pairs of 2 numbers like this. So basically, whatever is 2k minus 3 will be congruent to 2k plus 3, and also will be congruent to 2k plus 9 modulo 3, right? So in the same way, 2k minus 1 and 2k minus 5, they will be congruent, and finally these two will be congruent. So out of these 3 sequences, at least or exactly one sequence will be all 0 mod 3. So which are that sequences? If you are lucky and the sequence happens to be this one, like 2k minus 3, 2k plus 3, and 2k plus 9, in fact you will get 3 copies of 3, but that is not guaranteed always, but 2 copies are definitely guaranteed. So basically 3 square is always going to be a factor of their product. Okay, then what about 5? So again, in the same way, you can see that there will be at least one copy of 5 which is guaranteed in the product, and finally there is a copy of 7 guaranteed in the product. So the fact that there is a copy of 7 comes from the fact that this entire set, you can prove that this forms a complete set of residues modulo 7. So in fact, it will be that exactly one of these will have remainder 0, one will have remainder 1, etc. So therefore, exactly one of them will be multiple of 7. Okay, so I mean, these are the ones which you can guarantee. Anything apart from that, like 11, etc., there is no guarantee that it will be a factor. So therefore, the answer is simply the product of all of this. Okay, so 9 into 5 into 7, so that is 315. Okay, so this is I mean, in the realistically, I think this is much too simple for IOQM, but just to give you some quick practice, ideally in IOQM kind of environment, this could be the sub problem of a larger problem. So you are expected to finish this problem in less than 1 minute, you can say. Okay. So I hope everybody got the idea. And I don't think there is much alternate solutions available. I mean, it's a very straightforward calculation. Okay, so that was question 1. Question 2, each square of the board is colored white or black. So yeah, question 2 is actually I mean, the simplest version of a entire series of questions. So it's a good motivation to learn some of those topics right now. So I mean, actually, I would say those topics are kind of advanced for IOQM and maybe even for INMO. But I mean, basically, this is about counting under symmetry of various kinds. So that is what this question is about. So in this case, for example, it's a 2x3 board that is given. So you have 6 squares available to color white or black. So under no other condition, just allowing you to color anyhow you want, obviously the answer is 2:6, right? There are 64 possible ways to color all the squares white or black. But now the additional condition given is that if you have two colorings such that one can be rotated to form the other, then they are supposed to be considered equivalent. So for example, if you consider coloring like this and like this, so clearly you can rotate by 180 degrees to form one from the other. So therefore, they should not be double counted. So I mean, just to solve this question, it's simple to observe how many cases will get double counted this way. And if you get that answer, then you can solve this problem. So if anybody who has not tried this problem already, I'll just give you a few minutes to think that how you can eliminate those double counting cases.
Sir, is the answer 36?
No, I didn't get 36.
Okay, sir, I'll reach.
Can you explain your logic? I don't know if I made some mistake.
Sir, I found like similar one. Total is 2:6.
Yes.
So each one will be counted twice, but just the ones that are not counted twice, it are symmetric.
Okay.
So those one I added and then divided by 2.
No, wait. But which the ones you're adding are the symmetric ones, but the symmetric ones are the ones which are getting double counted, right? So the asymmetric ones are going to be counted exactly once. I think you might have which ones, because
I'll recheck.
yeah. For example, if let's say we color these 5 squares, then this is not symmetric with any other sequence. So this will get counted exactly once. So we don't have to divide by 2 for this sequence.
No, sir, actually, while what I did was I found the number of symmetric ones. I
Okay.
subtracted those from 64, then divided by 2 and added that again.
Okay.
So essentially, I like added and then divided by 2 to make them 1.
Okay. Let me think if there is some mistake.
Because in while we are in the 2:6, they have been counted only once only, the symmetric ones. So that's why to make them 2 times, we can just add them by once and divide by 2.
Yeah, I think you're right and my calculation is wrong, but let me understand properly. So we can draw this as a Venn diagram possibly that. So this is the set of all. Let this be the universal set of all 64 possible colorings. Okay. And out of that, we know that there are some colorings basically which can be paired together. So that basically one coloring is the rotation of the other coloring. So I mean, there is an entire set of such colorings which can be paired with some other coloring. And then apart from this, there is a set of colorings such that I mean, it is self-similar. So this is the set of colorings which under 180-degree rotations is equivalent to itself. So it will not get double counted with anything else. So for example, a coloring like this will go into the third set. So basically we have set A, B, and C. So A plus B plus C is 64. And obviously A and B are going to be equal in size. So 2A plus C is equal to 64. Now I think what now you are saying is you are counting the C, right? those which
Yes.
are symmetric.
And we have to find A plus C.
You have to find A plus C. Okay, so then what you are saying makes sense. So if we find C, so 64 plus C will be 2A plus C, and therefore A plus C is 64 plus C whole upon 2. No, I think then you are correct. So the answer you're getting is 36. So what is the count of C?
Sir, just a second. Count of C is 8.
8. Okay. So yeah, how do we get that? Which are all the symmetric ones?
Sir, we can just pair those, pair the squares. Like
Right.
what we have at the right bottom should be at the top right, top left,
Yes. Correct.
like that. So we have three
Yeah.
choices.
Correct. So basically, what we can do is we can assign the colors to the top row. So if we, let's say, assign the colors A, B, and C to the top row, and we are counting a symmetric case. So symmetric means that under 180-degree rotation, it should remain identical. So which means that it forces that if top left is A, then bottom right is also going to be A. So basically, once you choose the colors of the top row, all the colors of the bottom row will get uniquely identified. So therefore, the answer is, the number of symmetric cases is just 2 raised to 3, which is 8. Okay, for some reason I don't know why I did this and I thought this was the answer, but I missed something. Anyway. So yeah, so basically the set C has cardinality 8, and therefore A plus B together have 56, and therefore each of them has 28 each. So the answer is 28 plus C. So 8, which is
So what is A and B?
capital A and capital B.
Yeah, I didn't get that.
Okay, basically, if you consider any, I'll give you an example that, for example, consider this coloring, it's just the top left colored. This can belong to set A. And now if I just rotate this by 180 degrees, right, I'll get a new coloring which looks like this, which belongs to set B. So basically in the set A and B, there is a one-to-one correspondence by just rotating the board by 180 degrees. And what the question says is that under normal circumstances, you would count these two as separate cases, right? The first one and the second one. But the question says we are not supposed to count them as separate cases. We have to count them as only one single case. So the total size of A plus B plus C is 64. But in that we are counting A and B both separately. So we want to discount one of them.
And so C is like the C is also rotation, right? 180-degree rotation.
Yeah, C is the set of, basically what will happen, there are some cases where even after you rotate, you return back to the same configuration, right? So then that is not corresponding to any other. So for example, you take a coloring like this, right? So rotating this by 180 degrees will map it to itself. So this cannot be paired with any other combination. So
Okay.
all such cases will go into set C.
So these have to be counted back once.
These have to be, so everything in C has to be counted once also, and everything in A, if you count A and B both separately, then you have to divide by 2.
Okay.
Right? So then what we did was we counted the number of elements in set C, and that came out to be 8.
Okay.
So therefore we know all the counts now.
Okay, got it.
Okay. I would suggest you to practice a few more examples of similar types. So here because it was a 2x3 board, you can also ask the question, how many ways are there to count a color if, let's say, we allow mirror image, like horizontal and vertical mirror image. So for example, if a coloring like this is considered equivalent to the coloring like this. And similarly in the vertical mirroring. So basically every object has multiple what we call symmetries. So a symmetry is nothing but a function which modifies the object into itself. So basically for example, identity function. So the identity is just a operation of doing nothing. So the identity doesn't change anything at all. So any coloring remains identical. So that is the symmetry operation. You can have rotations. So rotation by 90 degrees, for example, let's say we are talking about counterclockwise rotation, then it will rotate it like this. You can have mirroring. So mirror in X or Y. So mirror in X might look like this will become this. And mirror in Y will flip it into this. So these kind of operations are available, and you can design lots of questions by choosing which of these operations should be considered identical and which should not be considered identical. So every such combination will lead to a different question actually. So there is a lot of variety in terms of how the questions can be designed along these lines. But in all cases, the special care that has to be taken is need to understand which combinations can be double or even triple or quadruple counted, and we have to divide by a suitable factor for those cases. Okay. So I mean the whole topic under which we will do this systematically is called group actions. Okay. And I mean, although it's not a very simple topic to jump into directly, and it's also overkill for Olympiad for the most part. I think you don't need something so heavy, but it's a very interesting piece of theory. So I don't know if I'll cover this today, but someday I will definitely would like to talk about group actions just to motivate some very nice mathematics. Okay, or if you want to read about this on your own, also there are some books. So there is a book called Enumerative Combinatorics, and that covers this very systematically with all the theorems and proofs. Is also George Martin. Yeah, this one. So George Martin, The Art of It. The full name is The Art of. Okay, so you can read about it from this book. It's a very interesting topic altogether. And now that you have time, I mean, there's no immediate exam pressure. You can use this definitely. But I would also like to cover this at some point, maybe not today. But I mean, the overall theme is just counting. You can call it counting under symmetry. Okay, so any kind of symmetry can be dealt with. You can also have kind of circular arrangements like beads on a necklace. I think you have done questions like this in the past. Like you have beads on a necklace and various rotations and mirror images are allowed. And what happens under those circumstances? More advanced questions can be like a object, like a cube, basically. If you have a cube and let's say you're going to color all the faces or the vertices, then again, I mean, you can imagine that a regular object like a cube has so many symmetries, right? You can rotate around so many axes, mirror image in x and y directions, and so on. So each such transformation can lead to a different question. So that there's a lot of rich number of possibilities to check in this. Okay. So this was question 2. Anybody else has any other approach for this question? See, if nothing else, you can just, I mean, 64 is not that big a number. You can just list out all the cases and just tick them off like that. But then there is a mistake of doing any mistake. So always a symmetric, like a systematic approach is always preferred. Okay, and question 3. Yes, Advait.
Where is the answer 15 by 4?
What is the answer? Sorry.
15 by 4.
15 by 4. I got an integer answer, so I am not sure.
Sir, I got 2 answers, but one of them is an integer which is not valid.
Not valid. Okay. Well, in what sense it is
Actually,
not?
I could not get this, but I tried this on GeoGebra, so the answer was getting to be 5.
Yeah, even I think answer is 5.
I could not solve it, but I tried this on GeoGebra.
Sir, I
Right.
got a quadratic whose roots were 15 by 4 and 5.
Okay.
And then we know that C by 2 is 3. So OC dash will be 4. 3
Right.
for 5 triangle.
Right.
So then CH will be 4 to the 8. But we get that the altitude has the length of the altitude is less than 8. So I ruled out that answer.
No, actually, I didn't get. You said CH is equal to how much?
4 to the 8.
Well, no, how did we get that? Oh, sorry, double of that. Sorry, I mean,
Yeah.
OC dash is okay. Okay.
But anyway, altitude from C is 6.5, right?
Yes,
6.25, I guess.
6.25.
So won't that work still?
No, I mean, basically, I think what he's saying is that, I mean, it cannot be an acute angle triangle. Is that what you are concluding? That may be the case. That is
That's
fine.
why it is given line DE.
Right. Yeah, basically, I think it turns out to be an obtuse triangle. So that is why it is fine for a CS to be larger than the altitude from point C. I think that is why you thought we should discard that route and consider the other route, is it?
Yes, sir.
Okay, interesting. Actually, I didn't even realize that there are two possible solutions to this question. But anyway, so can you outline what is your approach?
Yes, sir. So first, sir, can you draw the figure?
I mean, right now I'll draw the figure assuming it's a acute triangle, but shouldn't matter for most cases. Okay.
So we draw OC dash perpendicular to AB.
Okay.
AB.
AB. Okay.
And we join CH.
CH.
So, sir, we note that CO is perpendicular to DE.
CO is perpendicular to DE, correct?
And so CO is altitude of triangle DEC,
Yes,
which is similar to the original triangle.
correct.
And CF is 6.25 because area is 75/4.
CF is 6.25. Yes, correct.
So we use complete meaning of similarity.
Mm-hmm.
The length of the altitudes are in the same proportion as the length of the sides.
Yes.
So in the smaller triangle, the altitude CO is has length R, capital R.
Yes, correct.
So R upon 6.25 is equal to X upon R, where X is equal to OC dash. So X is the circumradius of triangle DEC.
No, can you slow down? We
Let OC dash equal to X.
let OC dash equal to X. Okay.
So CH is equal to 2X,
CH is 2X. Okay.
which is the diameter of circle DEC.
Yes, correct.
So circumradius of DEC is equal to X. And so circumradii are also in proportion of the similar triangle.
Oh, okay. So you're using the circumradius of DEC and circumradius of ABC should be in the same.
Yes, sir. Yes,
Okay.
sir. Is equal to X upon R. So R upon 6.25.
Yes.
And
Okay.
second equation is 3 square plus X square is equal to R square. A Pythagoras theorem in triangle AC dash O.
Yes, correct. Yeah, we can apply Pythagoras to that. Basically, we know this is 3, this is X, and this is R. So 3 square plus X square equal to R square. Okay.
And so,
Yeah,
sir, we
so we can
solve
solve. Yeah.
this system, and I got two answers. X is equal to 4 or 9/4. And from that, I got 2 for R. R is equal to 5 or 15/4.
Okay. Yeah, okay. I think this should be okay. And I mean, only the thing is that let me check why the second route is coming. Maybe I missed some case, but irrespective of that, I mean, the R equal to 5 is a varied solution. So if you face this in the exam and you know the answer is supposed to be an integer, so you can write R equal to 5. So just going back, I hope everybody is able to follow why we started with the claim that CO is perpendicular to DE. Is that something that everybody follows, or we should repeat that? So that is because CO and the CH are isogonal conjugates. So I mean, I think I also mentioned this some time ago, but not sure if everybody remembers. So in a triangle, we already know that the altitude and AO are isogonal conjugates, meaning that these angles are equal. So what that means is that, and in addition, we also know that if I drop the altitudes from B and C, right, and this triangle. Okay, so the altitude fit of the altitude, this triangle AEF is similar to triangle ABC, and not only is it similar, it is similar in the opposite orientation. So ABC are counterclockwise and AEF is clockwise. So AEF is actually formed by mirror imaging ABC in the angle bisector and with some dilation. So therefore, what happens is that when you mirror image triangle ABC, the line AH also gets mirrored into line AO. And therefore, what it means is that this line AO is going to be an altitude of triangle AEF. Okay, so therefore, this line AO happens to be perpendicular to AEF. Okay, or I mean, you can show it in a variety of different ways also, but this is a very useful way to look at it.
I didn't get it.
So basically, triangle AEF is similar to triangle ABC, right?
Yeah.
And not only it's similar, it is a mirror image kind of, because I mean, if you look at this, the orientation is reversed. So if I drop the altitudes, okay, so look at this triangle and imagine how will you construct this triangle AEF starting from triangle ABC, knowing the fact that this is like mirror image of each other. So what you can do is you can first take the mirror image of triangle ABC itself, okay, in the angle bisector. So if you take the angle bisector as the mirroring line, then B will go to some location like B dash over here, and C will go to some location C dash, and you will get a triangle like this. Okay. So this A B dash C dash is the mirror image of ABC in the angle bisector. And when you take the mirror image like that, what happens to line H, which was the altitude of the original triangle, that will also get mirror image into a new line over here, correct? And so now what is happening that this mirror image line, I mean, these angles are equal because of the mirror imaging. And we already know from basic angle chasing that in the original triangle ABC, this AH and AO are isogonal conjugates, which means that this line AD dash already contains the point O, the circumcenter of triangle ABC. So therefore, what, and obviously this line, this blue line is parallel to the red line. So therefore, if this is a 90-degree angle, in the same way, this is also going to be a 90-degree angle.
Okay.
So basically, AO, which joins A to the circumcenter of the original triangle, is an altitude of triangle AEF. Okay. And I mean, if this is hard to follow, you can show the same thing in much simpler ways also. Just by simple angle chasing also, you can see that, because what will happen, I mean, if you just consider,
We can consider angle AFE that is equal to C and angle BAO that is 90 minus C.
right, correct. DAO is 90 minus C.
Okay, I did that for A1.
Okay, fine. Yeah, I mean, I was thinking about this way, that basically if you just join AO, right, then we know this angle is 90 minus B. And in this triangle AEF, this angle is equal to B. So
Yes,
therefore,
that's the same thing I did for
so you did on the
F2.
left hand side. Correct.
Yes.
Okay, so Anushka, you want to follow this? That this angle is B, this angle is 90 minus B, therefore this has to be 90 degree.
Okay. So B is because B is angle AEF.
Yes, correct.
Okay.
That is because this is cyclic
Similar.
quadrilateral, right? This
Yeah.
BFEC is cyclic quadrilateral.
Yeah, similar.
Okay, so just to go over otherwise solution once more. So I mean, first we notice that CO is perpendicular to DE, and what is given to us is that the I mean, in general, the point O will lie on that this CO line, but because it is also lying on DE, therefore what we get is the OC, which is the altitude of triangle DEC, is also equal to the circumradius capital R. So the fact that OC is equal to capital R is what we want to use. And there, when you have two similar triangles like DEC and ABC are similar, so all of their features are going to be in corresponding ratio. In particular, their circumradii are also going to be in corresponding ratio. So if the circumradius of capital ABC is capital R, and the circumradius of DEC, which is half of CH, right? I mean, half of CH is basically OC dash, which we call X. So therefore, X and R are going to be the same ratio as any other feature that you can compare. So for example, here we compared R and 6.5, the altitudes. So that is how we obtained the first equation. And then the second equation through Pythagoras triangle AFO. Sorry, AC dash. So yeah, this is actually very good, like first principle solution. If you don't know any other theory, in particular, if you don't know any trigonometry, then this is a very nice way to do it. But if you just add a little bit of trigonometry, you can simplify a lot of the calculations. So let me just indicate how that can be done. So and although we have not covered trigonometry properly in our lectures so far, just want to indicate that trigonometry is not really some completely new topic. It's just an extension of geometry. In fact, you can think of trigonometry just as a convenience notation. Like when you say cos of angle A, all you're saying is that if I draw a right angle triangle whose one angle is angle A, then what is the adjacent side upon hypotenuse ratio? Such a big phrase can be just simplified as cos A. But apart from that, it is just a geometric notion. I mean, not to say that things are always easy with trigonometry. There is one particular difficulty with trigonometry which I will indicate. But for now, how to solve this question? So, in fact, let me draw it. Yeah, funny thing is actually even I checked this on GeoGebra, but I don't remember coming up with two solutions. So, don't know if I missed something. So in fact, I know at least two other solutions. So the first solution can go like this. So starting is exactly the similar way what I said. So this CO is equal to R is what we can assume. And now, I mean, I want to emphasize what is the ratio of similarity between the two triangles. So triangle DEC is similar to triangle ABC. But what is the ratio of similarity, if you know? So the ratio, it is cos C, right? So basically, cos C is to 1. So anything in the original triangle can be multiplied by cos C and you will get the corresponding length in the smaller triangle. So therefore, what it means is that OC is nothing but the original altitude, if I denote it by HC. So HC is the length of the original altitude multiplied by cos C. So this is OC and that is equal to capital R. So what we have is capital R equal to HC into cos of C. Okay, and now out of this, we are interested in finding capital R. We already know HC. So if we find cos C somehow, then we are done. And what is the information we know? We have R, HC. Sorry, we don't have HC or R. We have the length of the opposite side, right? Small c is given to us. So, I mean, something that we already know that in a triangle, you require 3 pieces of information to construct a triangle, right? So, in that sense, the 3 symbols R, HC, and small c, right? There has to be some relation between them, which we can exploit to finish this problem. So only difficulty seems to be that here you have cos c and here you have small c, which is the length of the side. So how to relate those together is not clear. So can
we can do that using sine rule?
Yes, correct. So what can you write?
Like sir, I was talking about relating small c and capital C.
Yes,
So
correct.
like small c is equal to 2r sine capital C, and
Yes,
that
correct.
sine capital C we can write root of 1 minus cos square C.
Correct. Exactly. So I mean now in these two equations, we know C, we know h of C, and we want to everything in terms of the R, which is the unknown variable. So the only burden is this cos C and sin C. So we just need to eliminate them. And then we just use the fact that cos square C plus sin square C is equal to 1. So I mean multiple ways of writing the equation, but for example, you can write R upon HC whole square plus C upon 2R whole square equal to 1. And now in this equation, the only unknown is capital R. And I think quite possibly this is going to lead to the same kind of equation that otherwise you were talking about. It might have 2 solutions, and then I want to check actually why we have
Here
almost.
won't we get a 4th degree equation?
Yeah, we'll get a 4 degree distribution, but it's again R square, right? So basically R plus minus R will be two roots like that. So we'll have two positive roots and two negative roots.
Okay, so we
So
can take
we
the R
can-
square as the variable.
Yeah. Basically, it's a quadratic in R square. Okay. Let us solve this. I want to check what is the second root that which I didn't realize. So and we have HC is equal to 6.5. No, you can write it as 25. So we'll get R square upon. Clear in denominators. Let R square be denoted by some variable X. So this is nothing but 4x square. 4. Yeah, whether I'm trying to do everything in variables as much as possible. I mean, only at the last minute where we cannot do any further calculation with variables, that is when we substitute the values. But until then, let's see what are as much as we're able to find without involving any numbers. That would be good. I think at this point, we just have to substitute the values. Again, the HC is 25 by 4. C is 6. It's, so therefore, the delta will turn out to be no, looks like I made some mistake because my determinant is negative. Oh, sorry. No, it's I 36 square. It's already square. that is therefore x is 4 times 25 square by 4 square plus. Yeah, so I think one root I'm getting is x is 25, which leads to the solution r is equal to 5. And the second case I'm getting x is equal to 25 into 18 by 30. Right. So in this case, I'll get r is equal to 5 into 3 by 4, which is 15 by. Yeah, I think it's a good idea to investigate what is the second root that we are getting. When Arnav in GeoGebra, when you draw the picture, did you get two possible positions, or you didn't consider that?
I didn't consider the second one. I just got the first one, and it turned out to be nice, so I didn't check out for the
Right, right.
second one.
Okay. Okay, so let's find out by inverting the problem, and this is something which can be done. Suppose I give you this question, given a triangle ABC such that it has this property that O lies on the line EF, and I give you the lengths of HC and C. Can you construct triangle ABC using ruler and compass? Okay. To construct triangle ABC with a ruler and compass given this information. So you have three pieces of information. You have two lengths and one relation, which can be somehow converted into the equation. So how will you approach that? Not EF, but
DE.
DE, sorry. Okay, so how will you construct this triangle with ruler and compass? And when we do that, obviously a sort of implicit question is how many unique solutions are you going to get? Okay, and you can try this problem independently, but I want to point out one more interesting property which comes out of this assumption. So the assumption of O belongs to DE. So I mean the way I approach the solution, if you go back, basically I said that R is equal to what HC times cos C, right? So let us simplify this further a bit because there is something very interesting that happens here. So try to get everything in terms of the sides of the triangle. So how can you represent cos C as?
A square plus B square minus C square upon 2AB.
Correct. And what about HC? I mean, you know, multiple areas, formulae for the area of a triangle. So triangle is of course half into HC into C, but is also equal to ABC by 4R, right? So therefore, with this, you can see that HC is also equal to AB upon 2R, right? So if you use that value over here, what do you get? In fact, AB and this AB will cancel in the denominator. And when you simplify, you ultimately get the equation 4r square is equal to a square plus b square minus c square. Okay, a very interesting fact. And in other words, also you can write as a square plus b square is equal to c square plus 2r whole square. And there could be lots of geometric interpretations of this fact. For example, you can think of it like if I considered a triangle, right angle triangle with sides A and B, and another triangle with side lengths C and 2R, then they will form this kind of they will have the same common diameter. So in fact, this will be like a cyclic quadrilateral. So there are like very interesting implications of this. And I mean, this is a very good equation. This a square plus b square to c square plus 2r square. Only problem is that I mean, if you think about it, it's actually looks like there are 4 independent variables, but we know for a fact that any triangle can be uniquely described by only 3 variables. So there is a 4th kind of redundant variable like 2r square which is coming here, but that can be useful in some context. And I am just indicating this because I'm wondering if somebody would like to use this property in solving this construction problem. Okay. So when you try to construct with ruler and compass, there could be some way to use this property which you can think about. Let me just try this in GeoGebra. I'm very curious to know.
Sir, actually, for the given data, the circumference is never becoming that 15 by 4. The least one is 5.845.
Right. Yeah, because actually the distance between the C and the opposite side will not allow such a small circle to be
Yeah,
formed.
because the circumference will be least when it is an isosceles triangle.
Right.
And at that point, the circumference is 3.845. I did that using the calculator.
Okay. And this is 3.75, so that cannot be. So oftentimes when we get this kind of a solution, right, a solution that we cannot seem to imagine on our plane, that is because we are dealing with what we call the real plane, okay, where every point in our plane has a real coordinates. But there is a concept called a complex plane where every point has complex coordinates. And actually we cannot even draw that plane on our paper, because if you think about it, if both x coordinate is a complex number and y coordinate is a complex number, then in some sense it is a 4-dimensional space. So a lot of these like extra solutions that we get are often happening in that complex space. But I mean, we don't think about it that way. Like even something as simple as a circle and a line intersecting, right? In our normal plane, there can be cases where the circle, you draw write the equation of the circle, you draw the equation of the line, and you find the roots. And if in reality they are not intersecting in the normal plane, you will get complex roots for their points of intersection. So that is indicating that those complex roots, I mean, those points do really exist, but in the complex plane, not the real plane. So this could be that kind of a situation. So yeah, quite possible that we will not get a solution, but I just want to check. And by the way, you can think of similar problems. Here I just took DE as one example, but there are so many lines. For example, you can take the angle bisectors where they meet opposite sides, and that can be your line DE. So like there are so many conditions that you can invent, and in each of these conditions, you can ask the question that what is the relation that you can derive in terms of the either the side lengths or the angles or anything like that. So that is a useful exercise to. I mean, whenever students say that we don't have enough practice material, that is because you need to spend time generating your own new questions from the existing questions. Like what happens if you modify one condition of the question, then suddenly you'll get a new question altogether. So if you keep doing that, then you will find that in fact there is no shortage of material at all. And in fact, that's a very useful way to discover the limits of your tools.
Sir, you have taken the wrong center.
Uh,
You have taken the
Oh.
center of 6.251.
oh, didn't I take the?
Oh no, yes, sir. Right.
No, I took the second center of
Yes,
this
sir.
one, right? I mean, if I move this, it is moved.
Yes, sir. Yes, sir.
So I mean, I guess the solution which we are looking for is this one. And in this case, as you can see, G is almost exactly at point the number 4. So that the circumradius GB is equal to 5. So that is the solution that we found. And what happens if I keep moving this away? Yeah, I don't see any other case where.
So
Yeah,
actually it just becomes, but it is not exactly.
Yeah, it looks very close, but it is not clear.
Because it is 3.8. The GeoGebra says
Right.
3.8. It's 3.845 at that time.
Right. Yeah. So I think we can safely say that the only solution in the real plane is the one we found. But just keep this point in mind whenever you are studying, particularly when you start studying coordinate geometry at a higher level, right? When you do things like hyperbola, ellipse, and things like that, you will often run into the situation that you have two equations which you can solve and you get roots, but those are complex roots. So I mean, the way you can think about it is that a circle and a line always intersect in 2 points. Sometimes they are two real points and sometimes they are two complex points. And sometimes those are, I mean, in the case of tangency, those are coincident points. But always the intersection set contains 2 points. Okay? So in that sense, there is a second solution, but it's not in our real plane. Okay.
So can you just scroll up to that solution of question 3, the construction one?
Okay, sure.
So for in the first thing, I written R is equal to HC times cos C, and we represent cos C because of the cosine rule, right? And R is like, I didn't get that equation, or where we get R from.
No, so what I did was cos C becomes this whole thing, and I look at HC. So HC, I mean, you know the area of a triangle as ABC by 4R.
Yeah.
And so if you equate it this way, what you get is HC is equal to AB upon 2R. And if you substitute that here, you see AB in the numerator will cancel with AB in the denominator. And so what will be left with is equation like this: 4R square equal to A square plus B square minus C square.
Okay.
Yeah, okay. There's one more solution which I want to indicate, which is it requires more calculation, but it does avoid trigonometry. So I mean, just for context, that questions like this can also be done without trigonometry. In fact, I mean, otherwise solution is one way to do it. But I mean, how to represent this condition in a different way? Like O belongs to DE. One observation which we had was that altitude length. But there is one more way to look at the same information. And for example, suppose you forgot the fact that those two triangles are similar. What you can do is still something like this. So basically, what we can exploit the fact that wherever that circumcenter is, right? O, if it lies on this line D, basically it also is the same as saying that this angle is equal to A, right? That is the equivalent statement. And therefore, what you can do is in this triangle, sorry, again, if I call this OC dash. So in this triangle, I can determine all the lengths in terms of the sides of the triangle or anything you want. And therefore, you can write the equation that OC dash upon CD is equal to, I mean, either you can write cos A or, I mean, what we know to be equivalent to cos A. Not, sorry, cos A, tan A. Right. So, I mean, you can use any other reference in the triangle which is tan A. For example, this angle is A, so therefore it means that AE upon B is tan A. B upon B, something like that. So, I mean, you can, if you don't want trigonometry, you can disregard tan A and you can directly write this is equal to this. But I mean, this is where I'm indicating to you that trigonometry is not some monster. It's actually your most helpful friend. So that if you just imagine if you didn't have trigonometry, you could not write that OC dash upon CD equal to tan A. You have to find some other reference triangle whose with right angle triangle whose one angle is A. Like for example, this triangle AEB that we considered, and then equate the ratios like this. So tan A is just like the way like in economy you have currency as a way to bypass the barter system. So in that way, trigonometry is allowing us to have a uniform sort of reference point without having to invent a new triangle. I mean, luckily in this case, this triangle AEB was present where one angle is A and the other is 90 degrees, but there could be some case where such a triangle is not readily available. So in order to avoid constructing that triangle on the side, the trigonometry just uses a convenient way of approaching that. The disadvantage or rather the downfall in trigonometry where you can get stuck is that it can seem like a lot of unknown variables. I mean, you can overwhelm your problem with too many unknown variables, and then you'll feel that you're just transforming from one variable into another variable without solving anything. So that is where it really helps to have clarity in terms of what is your independent information and what you want to achieve. So for example, in this case, it was very clear to us that small c, HC, and that fact that O lies on D. This was our independent information, and everything else has to be represented in terms of this data set. So if you have that kind of clarity, then you will not run into the problem of going around in circles with trigonometry, which can happen sometimes. So we'll see more examples of this in questions that we do in the future.
Sir, I think I got the construction problem.
Yes, tell me.
Sir, what we can do is first we will calculate cos C. So cos C is D upon C.
Yes.
So 2 times capital R is 2R is C upon sin C.
1 minute, sorry. Sorry, can you repeat your statement?
2R is equal to C upon sin C.
Yes.
That is equal to C upon root of 1 minus cos square C.
Yes.
So that is, we can just another substitute, so that C square upon root of C square minus D square.
C square, where do you get C square?
That did
Yeah,
C in the
okay,
denominator.
yeah.
Of course.
Yeah, okay, right, correct.
D square. So by constructing a right angle triangle, we can construct the below length, denominator length.
Yes, correct.
Then we are able to construct R.
Yes, correct.
And so now what we do is we just draw a circle with radius R.
No, wait. We don't know DE, right?
D is given, right?
We have HC is given. C, HC, and
O is on DE is given.
O. The fact that O belongs to D is given, not DE.
Oh, okay. I thought that the length D was given.
No.
Sir, over there, what have you written? Like, can you go scroll down?
Sorry. Which
Yeah,
part?
in the denominator, you've written root over C square minus.
DE square.
Oh, okay.
And if you just substitute this over here, right, and you clear the denominators,
Yeah,
you get that.
yeah, got that.
Yeah, I mean, you can think of this problem. I don't know honestly if this construction problem has any non-calculation approach, and you can always do the calculation which we did. I mean, I'm not sure if everybody is familiar with how you can add, subtract, multiply, divide, take squares and square root using geometric constructions. But if you do that, basically you can compute the length of capital R in terms of HC and C. And then once you have computed the length of capital R, you can finish the problem. But I don't know if that will be a very long solution. So some easier approach can be present. But anyway, I'll encourage you to think about that independently. Okay. But as I said,
HC and C, right? Like we will need some that third information also, right?
yes. So using the third information, we'll get an equation.
Yes, sir.
basically the same solution that we got for this capital R square, right? This formula. So the important thing to notice is that everything in this formula is constructible. Okay. All we are doing is doing some kind of addition, subtraction, square root, multiplication, division. All of these operations can be done using ruler and compass. So that is why you can find the length of x, which is R square. So we can find the length of capital R, and then you can construct the triangle that. And by the way, this is a valid way to solve a problem. In, let's say, in INMO, if anybody gets a construction problem and you can find that what are some unknown length in terms of the known quantities, and as long as these are the only operations you have involving. So I mean, famously, you know that you cannot take a cube root with just geometric compass, ruler and compass, but square root is possible. So you can just write that this quantity is constructible using ruler and compass. So that is a valid approach. But as I said, I mean, try to construct your own problems. And here D were the fit of the altitude. Just change the problem and see what happens if, let's say, the points D and E are the midpoints of the sides, or what happens if they are the fit of the angle bisectors. And in each case, I mean, you have so much variety that you can put the condition as O lies on D, H lies on D, G lies on D, etc. You have so many special points, and each I mean, there is no guarantee that each of these cases will lead to an interesting solution. Sometimes that can be a dead end also, that you either realize that it doesn't happen in any triangle at all, or even if it does, the resulting condition is so vague that it's not really very interesting. But in this case, for example, I mean, I at least I feel that is a square plus b square equal to 2r square plus c square is a very nice and kind of unexpected surprise, that this is a necessary and sufficient condition for any triangle to satisfy the O belongs to D condition. So yeah, so feel free to explore in this way. Okay, coming back to the problem set. So yeah, I mean, actually I had thought that I'll require 1.5 hours to do the first 3 problems, but turns out that, I mean, because we already given you some time to think, so we are able to finish it faster. So that's okay. So then we can move on to the second set. So question 4. Prove that there are infinitely many triples of integers ABC such that ABC divides a square plus b square plus c square. So for question 4 onwards will be kind of harder questions. So I mean, you are free to decide if you want to stay, continue, or you want to leave. That is fine. Okay. So anybody who has already found the solution of question 4? Okay, so let's start thinking about this question. What approaches we can think about?
Sir, I was trying using periodic value,
Okay.
but like what I reached was, if there exists for a prime, if is there exists another for a prime, if there are infinitely many squares of the type p raised to k minus 2, then we are, I think, close, not done, but somewhere we are getting something.
Okay.
But still, then some another what I did was I took a prime p and removed all its prime factors from ABC. So
Okay.
that used the other thing still remains. What is not p?
Right.
That's where I'm stuck.
Okay. Okay. So a couple of things that we can start by observing first. We are supposed to show that there are infinitely many solutions, but there is no constraint on us in terms of how you want to construct that infinite sequence. So there is a lot of freedom available to us, that how you want to go about constructing the possible solutions. And I mean, to make our life simple, I mean, there are 3 variables here, but nobody forces us to think in terms of 3 variables. Even if we fix the value of any one of them, let's say you fix c equal to 1 and you reduce the question down by only to 2 variables, if that family has infinitely many solutions, then also we are done, right? So, I mean, of course, when we start solving the problem, there is no guarantee that this approach will work, but at least that will simplify things for us. So, it definitely worth considering. So, let us consider what happens if, let's say, we fix c equal to 1. Okay. So, now we only have to consider the equation ab divides a square plus b square plus 1. And now, of course, still we don't know whether this reduced set of equation also has an infinite family or not. But if we find out that this has an infinite family, we are done. So now the question is, does this equation have an infinite family or not? So first thing I think we have to realize is that here, I think it's necessary that a and b have to be co-prime, right? Because basically what we are saying is a square plus b square plus 1 is equal to some k times ab. So whatever divides, if whatever is the GCD of a and b, right? You'll see that basically it divides 1. Therefore, d has to be equal to 1. Therefore, whatever is the solution of this equation, a and b have to be co-prime. And that's a good thing, because what that means is that this equation can be considered if and only if these two equations are separately satisfied. A divides b square plus 1 and b divides a square plus 1. So if we find two co-prime numbers ab such that both of these are satisfied, then it is going to be a valid solution of our original equation. Okay, so that looks like a good start already, but we are still nowhere near complete. I mean, it's not obvious why this kind of a family will have infinite solutions. But now this is where, I mean, one important thing that is useful in number theory especially is to start doing some small experiments. So I'll give you some time to think and try to see if you can find some values of AB which satisfies this family of equations.
Sir, I'm getting that this AB will not divide a square plus b square plus 1.
No, I didn't. What is your question?
Actually, was something I'm getting that AB won't divide a square plus b square plus 1 for any a and b.
Why?
So what I did was like let p be one of the prime factors of a. So let a is equal to p raised to m u,
Okay.
and p does not divide u,
Yes.
and b is equal to p raised to n v, and
Okay.
here n is greater than or equal to 0 because it can also be 0,
Yeah. Yeah. Okay.
and m is greater than or equal to 1.
So m is greater than or equal to 1 and n is greater than or equal to 0. Okay.
So periodic value of ab is m plus n.
AB is m plus n.
And
Okay.
if you so that is greater than or equal to 1, so p divides ab, that we can say.
Yes, correct.
And now we go to v. Oh no, sir. Oh yeah, if n is equal to 0, then it can take place.
Exactly. And in fact, that's what we are claiming, right? AB
Yes.
being co-prime. So if P divides A, then P cannot divide B.
Because if there exists a prime, then we will get that p does not divide a square plus b square plus 1. So
Right, correct. So are you able to find at least one solution for this system of equations?
Yes, sir. 1, 1.
1, comma 1. Okay, so
1, 2 also.
Okay, so if you start writing the ABC pairs, so 1, comma 1, comma 1 is a valid solution. Okay, 1, comma 2 is also a valid solution. So I think you will quickly realize that basically 1, comma x, comma 1, this kind of family has only these solutions possible, right? Because basically x has to divide 1 square plus 1. So there is only finitely many possible cases to try. So let me not write C every time, actually that is adding. Let's focus on AB only. We already have fixed that C is equal to 1. So we are only looking at A. So I mean basically with A equal to 1, what are all the possible solutions? I think we obtained that. So if A is equal to 1, B is either 1 or 2. Right? This is the first step that we can reach. And that is because I mean B has to divide A square plus 1. Which implies that B has to divide 2. So therefore B is either 1 or 2. So then moving on to the next case, suppose A equal to 2. Now what are the possible values that you can get? So 2 has to divide
1
B
and
square,
5.
1 and 5. And out of that 1 is already done. I mean AB is symmetric, right? So you can consider without loss of generality that B is greater than or equal to A. So therefore B is equal to 5 is the next possible solution. So 1, comma 2, 2, comma 5. And this is the only possibility. So we can move on to the next one. So suppose A is equal to 3. So 3 divided square plus 1. 3 divided 6 square plus 2. So therefore the only possibility is B is equal to 5, right? But this does not satisfy this condition.
Yes.
So therefore there is no solution available here. Okay. So B is equal to 4. So B can be only
Still
7.
no solution, sir.
Still no solution. Okay. Then next A is equal to 5. So 5 divided B square plus 1. B divides by square. So are you getting a solution here?
B is equal to 13.
B is equal to 13.
Yes, sir, we get the solution.
So, I mean, how many values do you want to try before you can start seeing there is some pattern? 1, 2, 5, 13. Do these numbers have anything in common? And also notice something very interesting. The B of the second solution is the A of the next solution. So 2 continued here, 5 became here. So your next guess, instead of trying all the values 6, 7, 8, 9, why don't you try A equal to 13 directly and see what happens?
For 13, I'm not getting any solution.
For 13, you are getting
Not getting any solution. Not
not
sure.
precision. Okay. So 13. What is okay. So 13 has to divide b square plus 1 and b has to divide 13 square. So that is 170, right? So what are the factors of 170?
170, 85, and 17.
Are you sure you consider all the factors?
Yes, sir. That's 2 into 5 into 7. Oh, 34 is also there. No, 34 is not there.
2 into 5 into 17, right? So
Yeah,
34
34 is there.
Yeah, and does it satisfy?
It has to. Yeah, it's this.
Yeah, it satisfies the first one. 34 square plus 1 is divisible by 13. So, do you know anything about these numbers? What are these numbers?
There they are these alternate Fibonacci numbers.
Yes, correct. So, this is the observation. You can, let's say, f0 is equal to 1, f1 is 1, f2 is 2, f3 is 5, 4 is equal to 8. Oh, sorry, I missed. Etc.
The 34 and 89 should work maybe.
34 and 18, is it?
89 should work.
34
Yes.
and 89 should work. Yes, correct. As per the same pattern. So, in general, what can you make the claim? I mean, if we define the Fibonacci sequence in this way, what will in general A and B be?
F2n and F2n plus 2.
Right. Okay. So, this is our claim that A is equal to F2n, B is equal to F2n plus 2, and C is equal to 1. This should form an infinite family of solutions. So, again, I'll give you some time to see if you can prove this claim. But I mean, this is a very typical INMO problem. Okay. Actually, I unfortunately, if I had found this problem earlier, I would have submitted it for INMO for this year for consideration. But it's already past the deadline to submit the problems. And now that I've discussed it with you, obviously I cannot use that problem. But this is a very typical example of how an INMO problem can work. That you are not supposed to oversolve the problem. Okay, you're not supposed to find every possible ABC which satisfies that equation, because that is not asked. You are just supposed to construct one infinite family, and you have to use the liberty to simplify your problem as much as possible. So setting C is equal to 1, trying these small numbers experiments, that is what led to this possible pattern. And now, of course, the challenge is still to prove this solution works, but we can do that. That is not the hard part. The hard part is landing upon this possible construction of this kind of solution. Okay. So, I mean, do lots of small experiments, simplify wherever you can. These are very important lessons to learn from a question like this.
Then for this, should we go to the formula for Fn in terms of phi?
I mean, you decide. I don't think that's necessary, because what do you want to show finally, that A already we know that they are co-prime, so it's enough to prove that F2n divides F2n plus 2 square plus 1 and vice versa. F2n plus
Yes,
2
sir.
square. If we show this, it's enough. So you can show this in a number of ways. In fact, if you remember, you can use something that do you remember the practice test which I had given? In that, I asked one question about Fibonacci sequence. I think Fn square is equal to Fn minus 1, Fn plus 1 plus, I think, minus 1 raised to n or something like that. Now, depending on where you start the sequence at 0 or 1, but something like this could be useful over here. In fact, I have the suspicion, but I'm not sure. I mean, assuming C is equal to 1, quite possibly that this Fibonacci sequence is the only valid solution in A and B. Because I have tried lots of experiments, but didn't find any other solution apart from this sequence. So that would be an interesting problem to solve. That so that there is no other possible solution. I mean, I don't know. I'm just assuming that because I did find a solution. So are we able to prove this? Let's say we start with the first one. So we start to write f of 2n plus 2 whole square plus 1. And remember, we are interested in showing divisibility by f2n. So we can do everything modulo f2n. Okay. So if you just write this as f2n plus f2n plus 1 whole square plus 1. And this will be congruent to f2n plus 1 square plus 1. Okay, do you see this? That you can simply drop f2n from the consideration because we are doing everything modulo f2n. Okay. So in fact, f2n, f of 2n plus 2 whole square is congruent to f of 2n plus 1 whole square. And now this is where I think that when this property that I mentioned should be useful. So basically, f of 2n plus 1 square is congruent to f of 2n, or not congruent, equal to f of 2n plus 2 plus minus 1 raised to every, so this is minus 1. So in other words, so f of 2n plus 1 whole square plus 1 is equal to f of 2n into f of 2n plus 2. And therefore this is going to be congruent to 0 mod f of 2n, right? Hello. ओके बरं आणि ऍक्च्युली माझा क्लास चालू होता एक अर्धा तासात पाठव. ओके. Okay, so do you see this that this is going to be congruent to 0 mod f of 2n. So therefore the first part is true. F of 2n divides f of 2n plus 2 square plus 1. And I think the second part should also be doable in the same way, but except that now we have to go upwards now. And here we were coming down from f of 2n plus 2 to a lower index, but now we have to increase the index. Basically, f of 2n square plus 1 has to be escalated. So f of 2n square plus 1, I guess it can be written as f of 2n plus 2 minus f of 2n plus 1 whole square plus 1.
We get the same expression, sir, that f of 2n plus 1 whole square is
Right,
plus 1
right.
is f of 2n into f of 2n plus 2.
Right. Because again, we can drop this term f mod f of 2n plus 2, and then this will, yeah, exactly. I mean, in one case we are using f of 2n, in other case we are using f of 2n plus 2, but everything else will remain same. Okay. So yeah, I mean that's it. I mean that solves the question, because now we have shown that this is a valid infinite sequence of solutions for the original ABC. And so I mean just keep this in mind that this is sufficient to solve a problem like this. The original question of ABC divides A square plus B square plus C square for in general for any ABC, that looks to be quite hard. I mean, I also don't have a lot of progress. I mean, if I don't assume that C is equal to 1, then there is so much freedom that it's really hard to bound the problem that way. But it's interesting to explore that. I don't know if anything useful can come out of that, but okay. So I hope, I mean, this approach is clear that how not only the solution but approach, that how you can simplify the problem in a systematic way, and do some experiments to get what you want. And particularly in the older INMO papers like pre-2012, used to get a lot of examples like this, where the problem looks very hard, but with some simple assumptions, you can make it very simple. These days, I don't know if you get many questions like this. Somehow the sort of the trend of problems has changed slightly, but still good to keep in mind. Okay, then the next question, question 5. Anybody to solve question 5? So if I drop this condition that no two tiles are congruent, then there is obviously one solution, right?
Two solutions.
Two solutions, yeah. I mean, horizontal and vertical. If you
Yes,
consider
sir.
it. Right. But that condition seems to make the problem suddenly somewhat challenging. So there are two possible approaches that you can think about this question. One is some kind of a recursive or inductive approach. That suppose you have constructed a solution for n cross n, can you somehow modify it slightly to make a larger board? So some kind of inductive approach is one idea. And second is you just as without the node tiles congruent case, you were able to construct one solution just by taking all the vertical strips of 1 cross n size. Similarly, you have to be a bit more creative and construct a general, I mean, directly show the construction for some n cross n. So both approaches are possible.
Yeah, I was trying using the recursive approach, but I could not
Mhm.
get any substantive progress.
So I think the important decision you have to take there is, if you are given the construction from n cross n, are you going to try to make a jump of only one? So from n to n plus 1 is a hard jump, but it doesn't have to be that way, right? You can choose how much you want to increase your jump by. So for example, somebody could think of going from n to n plus 2. And in that case, the only thing is that your induction base has to be larger. So you cannot start by only one value, but that's okay. I mean, first few small numbers you can construct explicitly anyway. So you can think about what is the right jump to make there. I'm not saying that n plus 2 is necessarily the right jump, but that is like one option. Because I mean, clearly you will realize that going from n to n plus 1 is very hard to do inductively, because like if you already have a n plus n board tiled, right? Okay. And now you are going to construct an n plus 1 cross n plus 1 board tile. So as such, the existing construction that you have of n tiles, you are allowed to add only one more rectangular tile, but there is no rectangular tile which will cover exactly this area. So this is like a very hard constraint to solve it this way. So going from n to n plus 1 is doesn't seem to be working out. Going from n to n plus 2, you can also think about that, but if you try it out, you'll realize there is a slight problem with that also. I mean, in a way, it can be done. So let's say this is an n plus 2 cross n plus 2 board. Okay? So in this n plus 2 cross n plus 2 board, you can choose some suitable sub area of n cross n, and we already know that that can be tiled using n tiles. So for example, suppose you consider area like this where you leave a margin of 2 on both directions. Okay, so this board can be tiled correctly. And now you have to add 2 more tiles to cover the rest of the region. So how can you construct those 2 tiles? So you can think of adding a tile like this, right? A tile over here. So the dimension of this tile will be 2 cross n. And you can add a tile over here. The dimension of this tile will be 2 cross n plus 2. Now the only difficulty is that you have to ensure that no 2 tiles are congruent. So this 2 cross n plus 2 tile will not be congruent to any existing tile, right? Because one side is clearly larger. But it is possible that this 2 cross n tile is congruent to some tile inside this red region. So can we avoid
Yes, sir.
that?
Like if we follow this thing, then when we go from n plus 2 to n plus 4, then the 2 cross n plus 2 style will repeat.
Exactly, that is the difficulty. That this construction directly contradicts the next step. Like when you try to expand this one more level, like necessarily you are going to run into a problem that like in the next stage, if you are going to add a new tile of size 2 cross n plus 2, and that is going to conflict with this tile. So therefore, going from n to n plus 2 this way is also not a very fruitful approach. You could, for example, nobody forces us to choose this original region in the corner, right? So you can think of it this way also, this n plus 2 cross n plus 2 region. You can choose the middle part as your pre-tiled version, but now you are left with the border on all 4 sides. And again, there is no way to add 2 tiles which will cover the border on all 4 sides. So there is a problem here also. But I mean, continue to think along this approach that I mean, with some more like creativity, you can solve the problem this way. Okay, so I'll just give you a couple of minutes to think. There is a okay, so n plus 2 doesn't seem to be working. Then what can we think about next? And in particular, observe why this solution, I mean the centered tile solution, right? The one I'm showing in the bottom left, where you have 4 margins left on 4 sides. The reason why this does not work is that we have only 2 tiles available, 2 extra tiles, and they are not sufficient to cover all these borders. So how can we get more tiles?
In the middle part, we can just apply 1 tile.
No, sorry, what does that mean?
Sir, like if we want many tiles in the middle part, you can just apply that as 1 tile and then try to construct.
Okay, interesting idea.
I was
So,
trying yesterday using that for what n to n plus 1, but it didn't work.
Okay, but I mean, in that case, you are not really using a recursive approach, right? Then that is like explicit
Yeah,
construction.
direct construction.
Yeah, sure. Yeah, we can do that. In fact, I'm going to show one approach with direct construction also, but the starting point is completely different. But let's think about what you are suggesting. So, I mean, let's drop the inductive approach. I mean, we just want to construct an n cross n board, and we start with the central single big tile, and now we are left with corner. I mean, the surrounding areas. And I mean now we have n-1 tiles to cover those surrounding areas. So it's not very obvious. I mean, obviously it can be done, but the uniqueness of, I mean, no two tiles being congruent At least
Sir,
right
and
now.
also in those constructions, the some parts have to add up to n because
Correct,
like you
exactly.
cannot have a tile around the corner.
Yeah, exactly, correct. Actually, you don't need any part to add up to n because you can have kind of swastik arrangement, right? I mean, you have tiles like this, and then this ends here, and then new pattern starts here. So there is no need for any of them to equal to n completely.
Okay, yes, sir.
This way. Obviously, but all of them have to be incongruent to each other, and that can be very hard to achieve. So I don't know about this approach, but I continue to think on the inductive approach. Like again, I can give you the answer, but just to give you some time to think that why did this n+2 not work? Because we were falling short of tiles. How many tiles would you like to have to cover this surrounding region? Clearly, 2 tiles are not enough. Will 3 tiles be enough to cover this border?
No,
No. But 4 tiles can be enough, right?
no, sir.
Why not?
Still they will be congruent, right? Because you'll
Yeah,
have to take n
congruency.
plus
I mean, yeah, congruency is a different problem, but even dropping the congruency with 2 tiles, there was a problem of coverage itself. Like
Yes,
the
sir, yes,
congruency
sir.
was not the bottleneck. There is no physical arrangement to cover this kind of a weird shape with 2 or 3 tiles. But with 4 tiles, at least dropping the congruency part, we can at least cover it, right?
Yes, sir.
Yeah, but yeah, I know that there is a problem of congruency. But now that gives us an idea that now if you want 4 tiles, then what should the jump be? We cannot go from n to n+2. It has to be
n+4.
n+4, correct? So now let's think about that. So now we have n+4 cross n+4 board, okay? And now in the center we have this n cross n region, okay? And now because this is of length n, which means that there is a margin of 2 left on every direction. In both horizontal and vertical, there is a gap of 2. Okay, and now this outer ring has to be covered with the extra 4 tiles that we have. We have to use them to cover this outer ring. Now, if we try to do in the normal like stick pattern, then obviously that will be an issue because again you are going to have all these 4 external tiles are going to be congruent to each other, so that will not work out. So I mean, just think slightly differently. What can be done?
And each tile should have at least one dimension greater than n+1, right?
Yeah, that would be very nice to have because then that solves the problem for us that newly added tiles will not be congruent to any of the existing ones.
Yes.
That would also be very nice to have.
Or else, sir, also we can that in the whole construction, none of the tiles should be n+4 and one of them can be n. Even that would work.
No,
Like
one of them can be n.
one
Then
of
there is.
like what we are in the ones we are constructing newly,
Mhm.
none of the dimension is n+4 and one of them can be n because then in n cross n does not occur, so it can occur in n+4.
But when you try to extend this inductivity to the next step, couldn't that be a problem? I
No,
mean,
sir, because there we will use n+4 and n+4 we have not used here.
but there we'll have to use n+4 and n, right? No, no, sorry.
So what I'm saying is that if you don't use x by x, then we can use
Mhm.
x in x+4, and but then in x+4 we can't use x+4.
But then, so that means that the same solution will not scale to every level because if I mean ideally it should be uniform construction at all values of n, right? It shouldn't have require a different rule depending on what is the value of n.
Sorry, it does not need that, right? Like if in the uh, if in the central tile none of the
Mhm.
n dimension is none of the n dimension is occurring,
Mhm.
then we can use n in the n by 4 class slash n by 4.
Right.
And
As long as we don't use n+4 dimension in the n+4 cross n+4
yes,
construction.
sir. Then
Okay,
for
got
n+8 we can use n+4, but not
Yeah.
n+8.
Correct. Agreed. So basically, what you're suggesting, let's modify the induction hypothesis. We claim that there exists a tiling of n cross n with everything else such that no tile has a side of length n. So if this is a new induction claim that we are trying to make, then that can be used. So again, the induction base has to be established, and then the induction hypothesis can leverage this to construct the next level without and in that next level construction also we have to prove that this same condition is being satisfied, that there is no tile of who has the same length as the original large square. Yeah, that is certainly possible. And I think there could be a solution along these lines. But I'm saying there is a solution without requiring this condition also. You can, your first assumption that let's have all the tiles greater than n in at least one dimension. That can also be achieved. But here it seems difficult, right? The way we have constructed it this way, you will say that, I mean, no matter what you do, there is not enough room to do a lot of variation. And clearly, along every edge of your original square, there has to be one tile. And if you don't extend that tile all the way to the end, like suppose if somebody has the idea, let's not extend the tile to the whole end of that row and leave a gap over here. Then to fill that gap, you need a tile like this. And then there is a gap over here. So that problem seems to cascade. But I mean, the only reason why this kind of complication is occurring is because if you do with the normal, like the most intuitive swastik pattern, there all the four tiles are congruent to each other. Okay. So, I mean, the strategy to fix this problem is the same that we used in the previous question, some kind of creative manipulation. What can you do to make these four tiles not congruent to each other and still solve the problem?
Excuse me, sir.
Yes.
Sir, I still didn't understand in one approach where n goes to n+2, where we had one tile of n+2 length and the other tile of say n length, 2 cross n and 2 cross n+2. Why isn't this means why won't this be feasible?
Right. So the difficulty in that approach is that, I mean, the diagram which we are showing here, right? So the original the inner, this one is of n cross n, and now we are constructing n+2 cross n+2 region, and for that we added these horizontal tiles that we added. I mean, the condition given in the question is that no two tiles should be congruent to each other. This is also something we have to ensure, right? So
Yes,
in this case, I mean, this left one tile is clearly larger than n in one dimension, so there is no risk of that being congruent to any of the existing tiles. But what about the tile on the top? So this tile, which is of size 2 cross n, it is possible that some tile in the interior of this red region was also of size 2 cross n. So then that will violate the congruence problem, right? And in fact, that is only one part of the problem. Suppose that somehow you can even construct a way inside this red rectangle, which does not have a 2 cross n problem, but this is induction. So now imagine what will happen when you go one step ahead. So now using the n+2 cross n+2 construction, using the same approach, you attempt to do the n+4 cross n+4. Now there what you will do, you will add one tile over here on the left side, which is of dimension n+4 cross 2.
Yes,
There is no problem over there. But now look at the tile you are going to add on the top. Its dimension is actually 2 cross n+2, right?
yes,
And that is exactly equal to this tile, which we already added inside.
yes,
So
yes.
now basically we are proving that this way of induction cannot work. So we actually have achieved the opposite of what we wanted to do.
Okay, sir. Thank you, sir.
But now here, I mean, the hint I'm trying to give is that I want to make these border tiles incongruent to each other somehow. How can I do that? How can I force them to be not congruent to each other? So there was a sort of an implicit assumption that we just, because it seems so natural and we did it that way. But if you think about it, who is forcing us to place this inner n cross n tile right at the center of our board? nobody said that we have to leave a gap of 2 in every direction, right? We can leave it in a slightly asymmetric way. So why don't we do it this way?
Like 1 plus 3.
Exactly. So let's leave a gap of 1 over here and 3 over here. And similarly 1 at the top and 3 at the bottom. And now see what happens. So the inner rectangle is still n cross n, and which we know we can tile using n tiles. So you realize that the same swastik pattern can be applied here also. So there will be one tile at the top like this, one tile at the left, and you can check the dimensions of all these 4 tiles. That none of them will be congruent to each other, and all of them are greater than size length n in one of the dimensions. So there is no risk of them being congruent with the inner red square also. Okay, so is this working? I think the first tile is of size 1 cross n plus 1. Second tile is of size 1 cross n plus 3. This tile is of size 3 cross n plus 3. And this is of size 1 cross n plus 3 cross n plus 1. So all of them are going to be of different sizes.
So now we just show for 1, 2, 3, and 4.
Right.
Like
Other question
3, 4,
starts
5,
from 3, 4,
3.
6. So if you just explicitly show construction for 3, 4, 5, 6, and with this approach of induction, then you are guaranteed that all cases will be covered. Okay. And 3, 4, 5, 6 are, you can show it easily. It doesn't take a lot of work. In fact, that should be a starting point. First thing is to do small experiments and prove it for small cases first. So for example, something like this for 3, for 4. And there is a lot of freedom actually. There is no probably multiple solutions available. And same for 5 and 6, you can construct something that is not hard. So so this was the inductive approach. But again, before we go to other approaches, just pause and think about how you're. I mean, I'm not interested in showing you what is the solution, but I'm more interested in motivating how you can think of the solution in the whatever time constraint you will have in the exam. So I mean, if you given sufficient time, everybody will think of all idea, but how to latch onto the right idea as quickly as possible. So, I mean, first is that we would like to use some kind of induction, and in that recognizing the important point that when we say induction, we always sort of latch onto the idea that we have to advance by 1 step. So from n we have to go to n plus 1, but we can be more creative than that. In fact, we can be a lot more creative. It's not just we have seen examples of that. You can go from n to 2n and then backtrack. That kind of ideas also there. But so here realizing that n to n plus 1 won't work, n to n plus 2 also won't work, and why it doesn't work is also important. Not just that it doesn't work, but it doesn't work because we don't have enough coverage of the border portion. So that motivates that let's think about n to n plus 4. And again, realizing that nobody is forcing us to place that tile in the center and leveraging that. In fact, I'm thinking that n to n plus 3 might also work because the way I imagined, right? Nobody forces us to place this red inner thing in the interior, right? Suppose we place it against one edge. So we can consider n plus 3.
Then in n to n plus 3, like we can't place it in the middle only, right? Because it has to be 2 plus 1 and 2 plus 1 or 3 plus 0 and like that.
Right. No. I mean, by middle, I mean the interior. It will not be symmetric, but it doesn't have to be in the interior also.
Okay, so you mean 2 plus 1 and 3 plus 0.
Something like this. So here you leave a margin of 1 and 2 and 3 at the top, and then no, but yes. So you have one tile like this, one tile like this, and one tile like this. But then the problem is that these side tiles are of dimension n, so there is a possible conflict with the interior. So that is the
Then in
problem.
the 4, we just get that familiar arrangement of every tile getting one vertex and ending before the other.
Yeah, exactly. That is very nice to work. So yeah, I mean, of course,
Sir?
this is
So in
yes.
the n+3 thing,
Mm-hmm.
sir, if the two tile, the width 2 tile, if
Mm-hmm.
it has a length of n+3, then won't it work?
Okay, okay. So all the way up to the top, something like this,
Yes, sir.
and then one more tile over here. Yeah, this will work. Yeah, correct.
No, sir, it fails for 1.
No, no, but it's a Gaurav, when you are there, the left hand side tile, this is still the problem, right? This is still of length n. So
Yes,
how
sir.
can we show? And so
Yes,
if
sir.
you try to fix that by increasing the length of this tile all the way to the top, then the region in the top will be of length n.
Yes, sir.
So one way
Then
or the
that will
other,
become a length. Yes, sir, yes.
yeah, I don't know if there is any other creative way to solve this problem. Anyway, we don't have to do it also. Okay, so this was the inductive approach. But now let's look at an explicit construction that, see, just as if we, as I said at the very beginning, that if we drop that congruence condition, then it's obviously we can see the solution as just have all the tiles vertically like this, and that is the end of the story. But now because of the congruence problem, we cannot use this solution. Now, but see if you can modify the solution a little bit and fix that problem. Like if you just imagine that you have a hammer and you just break every tile somewhere. So you just create a break in every tile at some point so that each tile gets split into 2 smaller tiles, such that all these individual parts are not congruent to each other. Obviously, there is a problem that we are increasing the total number of tiles. So, and if we break every tile into half, then starting from n tiles, we will be left with 2 n tiles. Whereas we are supposed to do the coverage with only n tiles.
Sir, we break some tiles and we combine some tiles.
Right, right. Or rather, I would say you start by combining the tiles and then you break them. So what if we first combine the vertical strips into, I mean, instead of having a only width 1, let's first cover the, and here let's say we can make cases for odd and even separately. So, I mean, we can come to that later, but suppose basically we first fill our board, let it be odd or even, doesn't matter, with size 2 tiles first. Okay. So now, so there are actually n upon 2 tiles to begin with. We are not using all the n tiles available, and that gives us the freedom to break every tile in half. So that after breaking into half, we will be left with n tiles, and sort of the point of breaking you can choose so that all the parts will be incongruent to each other, modular. I mean, incongruent to each other. Okay, so I'm just outlining the strategy. There are a lot of details to be filled, like what will happen in odd case, even case, and how will you ensure that no 2 parts are congruent. But you can work out those details. So I'll give you some time to think and complete the problem this way. But I mean, the important takeaway is that wherever you are this kind of prove that there exists a solution, you have to exploit your full creativity over there. That you can come up with any configuration. See, both question 4 and 5 are similar that way. The question 4 also was saying that you just construct one solution or one family of solutions. And the same way question 5 is that you construct one tiling, no matter how you do it. So, I mean, exploit the creative freedom that is given to you in this question. Okay, so are you able to do this construction? We can consider odd and even cases separately, because that would make things simpler. In fact, I think the odd case is simpler to deal with than the even case. So let's say a 2k plus 1 cross 2k plus 1 board. Okay. So first we have to do some initial tiling before we start breaking the tiles, because ultimately we want to use 2k plus 1 tiles. So I mean, in terms of pairing, there will be one tile which will be left as it is without breaking. So we can put that tile at the left side. Let's say this is the first tile of size 1 cross 2k plus 1. Okay. And so the rest of the board will first tile in like width of 2 each, right? So we have these k tiles of size 2 cross 2k plus 1 each. And now each of these tiles, if we exactly split it in half, I mean not exactly half, but in 2 pieces, then we can get all the 2k plus 1 tiles that we want. So I mean, obviously the idea we can use is you start from the top. So the first split you will make at the length of 1 from the top. The next split you can make at the length of 2 from the top, etc. So in general, every column, the kth column or the ith column will be split at the length of I. So the ith column will be split into one tile of size 2 cross I and another tile of size 2 cross 2k plus 1 minus I. Right? So you will get all such tiles where I goes from 1 to k. So if you actually write it out, actually you will realize that you will get one tile of every size and there will be no multiple size, right? So all the way from 2 cross 1, 2 cross 2, 2 cross 3 up to 2 cross 2k. Exactly one tile of each shape will occur without any repetition. Okay, so this is the odd case. What about the even case? So when you put it this way, this looks like a very simple problem, right? I mean, just you are going to, we have explicitly shown the construction. Don't even have to go into the complications of induction and all of that. So actually, this is not that hard of a question actually. Actually, I would say the previous one, ABC, is kind of harder probably. In the even case, I mean, in the odd case, we could start with this one like small tile left over at the left hand side. In the even case, we won't do that, right? So in the even case, we'll directly tile your original board in like width of 2 tiles, so 2, etc. So you'll be left with exactly k tiles of width 2 each. But now you'll realize that if we start to break these tiles in the same way, what will happen? So the first tile will break in at the gap of length 1. So the first tile will be of size 2 cross 1 and 2 cross 2k minus 1, because the length is 2k. So in that way, if you continue to break the tiles, then the next 2 tiles will be 2 cross 2 and 2 cross 2k minus 2. So what will happen?
So we will attain symmetry after the halfway done.
Yeah, but where are you going to be reach the half point?
Kth position.
Right. Basically at the last position, right? Just before the last position also there is no problem, because there you will get one tile which is slightly larger and one tile which is slightly smaller, right? At the k minus 1 position, the size of the tile will be 2 cross k minus 1 and 2 cross k plus 1, which is also fine. But the very last segment which is left now if you break it exactly in the middle, you will be left with two portions of length k each, which is a problem. And not only that, now this tile, no matter how you split it, right? I mean, so to avoid that splitting into two equal parts, you decide to split it somewhere else, let's say. But no matter where you break it now, you will be left with a piece which is congruent to some piece which already is occurred. So it seems that there is no way to split this last tile now.
Even vertically won't be possible
Even-
because
Correct.
again congruent tiles.
If you split it vertically, you will be left with two congruent pieces. So what do we do? But the approach seems so promising, right? So there is some small modification which can fix this problem. And I mean, always try to make the modification as small as possible. So if we split this last time vertically with the red dotted line which I have shown, we are getting two parts which are congruent to each other. Those are the only two congruent parts. So once again, we have to make them incongruent somehow.
So what if we split them vertically only, but if we not around the midline as such?
No, but it is of the size 2 only, right? This is a width 2 tile. So we cannot split it into non-integer parts. If only it were a slightly larger tile, then you definitely
Yes.
do it. So why is it not a larger tile?
Like or else since we divided into two, we can divide it into something k or
Right, exactly. Why don't we just make this small? I would like this tile to be of length 3 instead of 2. So only the very last tile, instead of having of size 2, I will have the very last tile of width only 1. So that now this remaining tile is of width 3, and that I can split asymmetrically. And this width 1 tile I'll split in the same way as before. So like whatever is the asymmetric way. So basically the last tile will not be of size 2 cross k minus 1 and 2 cross k plus 1. It will be instead of 1 cross k minus 1 and 1 cross k plus 1. And that leaves me the remaining two tiles which will be vertical like this. So one will be of size 1 cross 2k, and another will be of size 2 cross 2k. And while doing this reduction, because we are only reducing one dimension, I think it is pretty self-evident that there will be no two tiles which are congruent to each other.
So in this case, can't we divide horizontally as well, because now the width is 3 instead of
Yeah,
1?
we can divide it horizontally, definitely. I mean, now we are free to divide this anyhow we want it. So, but we cannot divide at the center. We have to just divide at some off-center location.
Yes, sir.
Yeah, we can do that definitely. So yeah, I mean, once you start thinking, there is a lot of creative approach is possible. Okay, so this was the even case, and we already did the odd case, so that should solve the problem. Okay, so yeah, again, just think about both approaches, the inductive approach and this explicit construction, and what you're learning from that, how you can apply creativity in different ways, especially in this kind of construction problems where prove that some solution exists. So you will find a lot of these kind of problems in older INMO papers. Okay. And again, just try to think of what variations you can add to this problem. Now, I mean, in the question, I've said exactly n rectangular tiles. What is so special about n? I mean, you could flip the question and ask, what are all the possible values of k such that you can tile the board with k tiles without any two of them being congruent? So you can come up with the entire solution set of all such values of k. In fact, first thing you do is that you will forget the congruency condition. If I just ask you the question that you have to tile an n cross n board with k tiles, k rectangular tiles, then what possible values of k are there? I mean, in the most extreme case, k can be only one because you cover the whole board with one tile. And in the other extreme, you will have all like unit squares, 1 cross 1. So then k can be n square. But can k take all the values in between or not? That is without the congruency condition. But once you add the congruency condition, then how does that possible solution set of k change? So there are a lot of various questions that you can create from this starting point, and you can explore them and see what you find. And sometimes you'll reach a dead end that you try to make the problem as hard as possible, and at some point becomes so hard that you cannot solve it. But that's okay. I mean, the point is to learn the process of applying these techniques in that. Okay, then question 6.
Sir, what I'm trying to prove in question 6 is that a square cos square a plus b square cos square b plus c square cos square c is less than or equal to a square plus b square plus c square by 4.
Right.
Because because you know that 9r square is greater than equal 9r square minus a square plus b square plus c square is greater than equal to 0.
Right. Okay. And I mean, the condition that you stated, do you see that it is reaching equality for a equilateral triangle?
Yes, sir. Yes, sir.
Okay, so I think most likely you are on the right track. But
because d in equilateral triangle d is a by 2, so that d square becomes a square by 4 only.
right. Okay. Yeah, question 6 is actually very heavily trigonometry driven. I don't know if there is a lot of non-trigonometry way to approach this kind of a question.
So actually, in many geometric inequality problems, trigonometry is used, right? Like,
yeah, it is there because I mean, ultimately trigonometry converts the problem into sort of calculation domain. I mean, at that point, it is no longer a geometry problem. It's just an algebra problem, right? So trigonometry is one of the easiest ways to make that transition. Not necessarily, actually. I mean, basically, ultimately, you have to choose some set of independent variables. If you want, you can choose the side lengths of ABC and express in terms of that. But that can be unnecessarily complicated, right? I mean, even in this question, the capital R, if you decide that I don't want capital R in my problem, and you decide to write everything in terms of side lengths of ABC, and the expression of capital R in terms of ABC is so complicated that, I mean, for example, you could use Heron's formula to write delta. So delta is whatever root S into S minus A product. And then that is equal to ABC by 4R. So that is how you can write capital R in terms of purely the side lengths ABC, but that is such a unwieldy expression to work with. So you avoid that, and to avoid those kind of things, trigonometry usually is a very good way to proceed. Okay, so even before we jump into trigonometry, we have to realize something. What is the most simple simplification that you can do of the question? Because first look at the geometry before you look at the algebra. Because what is we are supposed to show is d square plus e square plus fd square is less than equal to 9r square by 4. But what are points D, E, F? And what is the relation of those points with the value of capital R? Is there something that connects these two things together? Triangle DEF and capital R. What is the circumradius of triangle DEF? What are these points DEF?
Okay, sir. Sorry, sir. It's R by 2.
Yeah, I was
9-point
wondering
circle.
where everybody is lost there. Yeah. So yeah, I mean, you see DEF, I can forget about triangle ABC completely. I can restate the problem as I'm given a circle of radius R by 2. And in that there is some points DEF. And it's not hard to see that basically this inner triangle can be any triangle I can choose. And I can start with this 9-point circle of size R by 2 and choose any 3 points DEF, and from that I can construct my original ABC. So I can completely forget about ABC and look at only DEF. And so now really the problem is in this circle of radius R by 2, show that for any triangle DEF this condition is true, right? And I can go one step further and drop the. Why am I talking about R by 2 here now? Because now I don't have to think about it in that way. So let me redefine R by 2 as some new constant, let's say T. So now the question is, you have a circle of radius T, and now prove that in any triangle inside that circle, the sum of D square is less than equal to, now it will be 9T square, right?
Yes, sir. This was the result I was using for the previous substitution.
Right, correct. So are you able to show this result then?
Yes, sir.
Then you're done, right?
Yes, sir.
Oh, interesting. So I mean, you're almost completed, but okay. So can you outline the solution for us?
Sir, we calculate OH square in a triangle.
Yes, OH square.
By the cosine rule in
Yeah, I
triangle
think it's A
OAH.
square plus B square plus C square minus 8R square. I forgot.
It's 9R, simply 9R square minus A square plus B square plus C square.
Yes, correct. Okay, so then what do we do from there?
So directly we 9R square is greater than equal to A square plus B square plus.
Oh
C.
yeah, sorry. Yeah, okay, sorry. Obviously. Yeah, that's all. But then the question is, how do you get this formula? I think you just apply cosine rule in triangle AOH, right?
Yes, sir.
Yeah. So I mean, for those who have not done this, this is a good exercise to try that. Apply cosine rule and do the simplification to come up with this formula. Oh, I didn't realize that such a simple proof is there. But suppose somebody doesn't realize this, and then how do you do the problem like this? So it's a good way to look at what are the various algebraic manipulations that you can do to achieve an inequality like this. So we will look at that. And for convenience, let's not call it DE square, where there is no reason. We can call it ABC. Forget about the original triangle and look at this as only our triangle ABC. So in this, I want to show that sigma AB square is less than equal to 9R square. Okay. So if you just start to write it in terms of trigonometry, and why is trigonometry useful? Because see, I don't care about the dimensions of my diagram here. Like the capital R is just a scaling factor, so I won't like to get rid of that completely. So if I just divide by R square everywhere, this is sigma AB square by R square is less than or equal to 9. And now this AB square by R square can be converted into the trigonometry. So this is simply sigma of sine A sine square A. So in other words, I want to maximize sum of is sine A square plus sine square plus sine square A plus sine square C, right?
So
So I
it's
want to
not
max-
sine square, right? Because AB by sine is 2R, so that's
It is sine square, right? If AB is 2R sine A, so AB upon 2R is sine A, sine C. And
so we are taking R square only, right?
no,
So that's 4 sine square.
oh, so okay, I understand. So the constant will come there.
Yes,
That
4 sine square will become.
4 sine square, yeah, that is fine. Yeah, actually, I'm just looking at dropping the constant. What is just the maximization? So what is the value of ABC for which the maximum will be attained, no matter what the maximum is. So that is how I'm looking at the problem, so that we don't have to worry about the constants there. Okay, does that make sense?
Yes, sir.
Okay, so the job is to maximize sine square A, or rather find a triangle for which this will be maximized, and then for that triangle we will compute the original expression. Okay. So to maximize sine square A is the same as to minimize sigma cos square A. Correct? So to minimize cos square A, and now to minimize cos square A is the same as to minimize 2 times cos square A. And we know the formula cos of 2A is equal to 2 cos square A minus 1. So therefore, it's enough to minimize sigma of cos 2A. So in other words, we want to find the minimum of cos 2A plus cos 2B plus cos 2C. Or rather find what are the values of ABC for which this is minimum. And where we are going to use the fact that 2B plus 2C is 360. So which means that I can substitute 2C with 2A plus 2B. So therefore, I want to find the minimum of cos 2A plus cos 2B plus cos of 2A plus 2B. So you see how we got rid of one variable. I mean, this ABC are dependent variables. They are not, all three are not independent variables. And so now we are left in purely A and B, which can be treated as independent variables, because you can choose A separately and B separately. There is no restriction. I mean, of course, the restriction of their sum being less than 180 degrees is there, but we can disregard that also for now. And in fact, then why don't we talk about, instead of 2A and 2B, we can where it's occurring everywhere, we can just say let 2A be equal to X, 2B equal to Y. So now we just have to minimize cos X plus cos Y plus cos of X plus Y. Okay. Where X and Y can be any real numbers, in fact, in the most general case. So how to find the minima to this? So let us open up this and write it as cos X plus cos Y plus cos X into cos Y plus sin X into sin Y. Okay. And now
Minus sin X, sin Y, no?
Oh, sorry, minus. Okay. So now we have this expression consisting of two variables. So one trick that we can use is that let us fix one variable. So let us say that X has some fixed value. So for a given fixed X, what should be the value of Y to maximum or minimize this expression? Okay. Let's look at the problem that way. So for a given X, so let's consider X as a constant from this point onwards. So anything that is derived from X is also constant. So to minimize this expression, we can simply disregard cos X for now, and we want to minimize just this part. Okay. And with some regrouping, what we'll get is we want to minimize cos Y times 1 plus cos X cos Y minus sin X into sin Y. Okay, so here Y is the only variable, everything else is a constant. So I don't know if you are already aware of this thing. So in general, if A cos theta plus B sin theta is there, what is the minimum and maximum value of this expression? Is that something you already studied somewhere?
So 1, right?
1?
No, sir, no, sir.
No. Okay, so if not, you have not done this problem, I'll give you some time to think, because this is itself an interesting problem. For A cos theta plus B sin theta, try to find the min and max limits of this, where A and B are any real numbers. These are given constants, so A, B are not the variables, theta is the only variable.
So when theta equals cos inverse of A by root of A square plus B square.
Yes, correct. And what is the minimum maximum value that you can get?
Maximum is root of A square plus B square,
Correct.
and minimum will be negative of that.
Okay. So the trick here is to look at this expression and compare it with a standard formula such as sin alpha cos theta plus cos alpha sin theta, which is the expression of sin of alpha plus theta. Okay, so if you compare this term by term, it seems that if we can find the value of alpha such that we can make this connection, then this is simply a sine wave, and the sine wave is well known to be constant within 1 and minus 1. And so the only difficulty is, can there exist an alpha such that sin alpha is equal to A and cos alpha is equal to B? So in general, not, right? Because A, B are any real numbers. But so therefore, to force that, basically sin alpha and cos alpha can be any values as long as sin alpha square plus cos alpha square is equal to 1. So right now, A square plus B square is not equal to 1, most likely. So we would like it to be 1. So we have to multiply and divide by a suitable factor. So that motivates the idea. Let's multiply and divide this original number by root A square plus B square. So we can write it as root A square plus B square times A upon root A square plus B square into cos theta plus B upon root A square plus B square into sin theta. So now, once you do that, now these both expressions are such that this square plus this square is equal to 1. And therefore, by applying the inverse trigonometric functions, you can see that there exists some angle alpha such that sine of alpha is the first term and cos of alpha is the second term. So therefore, your original whole expression becomes simply root of A square plus B square sin alpha cos theta plus cos alpha sin theta, which is sin of alpha plus theta. And now this will be, just the sign itself is between 1 and minus 1, but with the multiplying factor, the actual expression becomes between root of A square plus B square and minus root of A square. Okay, so this is a good side information to keep in mind, that this is how it happens. Okay, so
Yes, sir. The one I said was for the specific for when A and B are also sin alpha and cos alpha of some.
right, correct.
Like there was a problem I read that prove that for theta sin theta into cos theta is less than or equal to 1/2 always.
Yes, correct.
There you use this thing.
Yeah, so this is the most general case of that kind. So applying this in our problem, right? So here we are looking at this expression, the one I have highlighted. So after regrouping, we get cos y into some constant and sin y into some constant. So the value of the whole expression, and remember you want to minimize it, right? You want to find the minimum. So what is the minimum value that can come for this part?
1 plus cos x whole square plus sin x whole square.
Yeah, and minus of that, because this value will be minus of root 1 plus cos x
Yes.
whole square plus sin. Okay. So this is the
That's 2
minimum.
plus 2 cos x, right?
This is 2 plus 2 cos x, correct? And so this was for given value of x. This is the minimum possible value of this part, and plus we are going to add cos x to that. So overall, now the question is, we want to minimize cos x plus or rather minus root of 1 plus cos x whole square plus sin square. Right? And we want to find what is the value of x for which this value will be minimized. Okay. So at what x will this be minimized? So as you said, we can simplify this bracket as this is simply 1 plus cos square 1 plus 2 cos x plus cos square x plus sin square x. Now here this is simply 1. So this is simply root of 2 plus 2 times cos x. Can you simplify this further?
Yes, like 2 we can so that's cos x minus root 2 root cos x. Then we can
No, actually there is a half angle formula, if you know what is cos of x upon 2. Because 2 cos square x upon 2 minus 1 is equal to cos x. Therefore, cos of x by 2 can be written as
cos x plus 1/2.
yeah,
Root of that.
Yeah. Okay. So in that terms, if you see here, I can pull out a copy of 2, and this is simply cos x minus 2 times root of 1 plus cos x. No, sorry. Yeah, 2 times 1 plus
Cos x by 2.
by 2. So in other words, this is cos of x by 2 minus 2 times cos of x by 2.
Cos of x minus 2 times.
Yeah, cos of x minus. Okay, and we have to minimize this. So now here this part is cos of x by 2 and this is cos x. So we should bring everything in the terms of the same variable. So why don't we write this cos of x also in terms of cos of x by 2? So this will be 2 times cos square of x by 2 minus 2 cos x by 2 minus 1. Right? So this is simply a quadratic in cos of x by 2. And where will the minima be achieved?
At the vertex.
Yeah, so basically minus b by 2a.
Yes.
So minus, so basically cos of x by 2 at the minima should be equal to minus of minus 2. So plus 2 upon 2 into 2, which is half. So cos of x by 2 is half. So you can see that therefore x by 2 has to be, for example, one solution is x by 2 is 60, for x is 120 degrees. Okay. And now you can plug this value back all the way into what we did. So I think x was 2a. In other words, a is equal to 60 degrees is where you get the maximum. And I mean, from that you can work out the rest of the variables like a, b, c, and all of that. Okay. Anyway, I mean, this was a very long solution, but just to indicate what various manipulations can be done at every stage. I mean, in this question, we were lucky that the OH square was directly able to give us the final expression, but in some other question, we may not be so lucky. So we should know how to manipulate these expressions to get what we want and sort of keep simplifying at every stage. So like the first simplification that we did was we got rid of we get everything in terms of ratios so that the actual lengths don't matter. So once it is a ratio of one length upon another length, it can become a trigonometric expression. And then from that, first thing was to get rid of the square root. So instead of sine square, we got something in terms of linear expression. Then removing the dependency between A, B, and C. Why are we working with 3 variables where we can work with only 2? So getting rid of C to get this kind of 2A plus 2B. And then once we have that, like cos x plus cos y plus this whole thing, then another important step was, when you have 2 variables, fix 1 variable at a time, optimize on that axis, and then go to the other axis. I mean, just to show this pictorially, you can show it in some way like this, that suppose like when you have 2 variables and a function of 2 variables, it has to be drawn in 3D coordinates, right? So basically this could be the x coordinate, this could be the x coordinate, this could be the y coordinate, and this is the f of x comma y. So what we did here was, when we said that let's choose a value of x. So when we choose a value of x, we're basically restricting ourselves to the plane, the 2D plane, which is perpendicular to the x-axis and passing through this point. So basically this kind of a, so we are only looking at this plane in which the value of x is constant. And now it is a single, now it is no longer a function of 2 variables because x is fixed. So now it is simply y in this direction and f of y in this direction. So for this particular plane, we find the minima. Okay, what is that minima point? And now once we have done that, now we go back to the original, we find the, so there are 2 ways to do it. We either find the value of y at which the minima is attained, or we find the minima itself. So for example, in this question, we were looking at the minima, the value itself, not the y. So in other words, we are plotting f of y on this axis. Okay, and once we do that for every value of x, right, basically you are going to get a graph of those minima themselves. So in terms of x, for every x, we know what is the minima attained. And so now again, this is like a question of, along all the values of x, what is the minima of that? So that is the global minima of overall x and all y. So this kind of two-stage simplification is what we are doing here. So I mean, this is something that can be useful in some other problem also. And then while doing the actual simplification, we exploited this linear of cos x, cos y, and sin y kind of pattern, where we could apply this root a square plus b square limits on both sides. And I mean, the rest of this calculation. But I mean, see how every time, even here, like at the end, when we were getting cos x and cos of x by 2, we try to get rid of 2 variables and bring everything in terms of a single variable. And so we keep doing that repeatedly at every stage. Okay. So in fact, there's a lot of variation possible of this question, same as before. So here D, E, F were chosen as the fit of the altitudes. Very interesting property which we are discovering just now. It is there in literature, but instead of taking the fit of the altitude, let's take the angle bisector. Okay. And now D square plus EF square plus FD square is less than or equal to what? This is a very completely unexpected thing, but the maxima is exactly the same. And it is attained at the equilateral triangle, of course. So, I mean, I don't know, very interesting coincidence that even for this triangle, the upper limit is the same. Actually, even I have not proved this completely, but I have observed this using GeoGebra. But this is a very interesting property which you can try to think about. And in the same way with other kind of special points that you can take. And not only the maxima, where you can think about the minima also. Okay. But anyway, I think that is all that I would like to discuss. Yeah, we are kind of quite early, but that's okay. I mean, realistically for me, it's hard to find more than 6 problems every week. So even if we have to end the discussion early, that is fine. But along the process, we will like sort of, as I said, I don't want to teach any theory explicitly, but along the way, whatever little bits of information or theory that we come across, we will study them in the process. Okay, so again this week I will send you the problems in advance, at least few days, so that you will get a chance to try them out. And in the meanwhile, if you come across any interesting problems or even generalizations of the problems we are doing, then keep sending them to us. As something I indicated in the very first lecture of our course, that constructing problems is a very important technique to improve your problem solving abilities. So keep doing that as much as possible and keep sharing that with everybody. Okay, I think that's all for today. Thank you.
Thank you, sir.
Bye.
Bye, sir.